Greetings. In this video example, we will be looking at the concept of free body diagrams, also known as force diagrams. So here's what we'll do for this example. We'll create some free body diagrams for the following situations. We have a car at rest, a car accelerating forward, a car at a constant velocity, and a car coming to a stop. Alright, so let's look at a car at rest just to start things off. Have the road, and within my limited artistic abilities, we have the car. Now, the components that are common to all free body diagrams are as follows. First is, feel free to draw, like I have right here, a sketch of the object, whatever the object might be. But at the center of the object, or as close to the center as you can estimate, go ahead and place a dot. See if I can make that a little bit bigger. Okay, now that's maybe a little bit large, but I just want to emphasize the point here. So we place a dot here in the center of our object, and this is where we're going to draw the arrows of the various forces that are acting on the object. Remember that when you are doing a free body diagram, you must only draw the forces that are acting on the object. You do not need to take into account any forces that the object is causing on some other object. For example, if this car would be pressing against a wall, we do not need to put the force on the wall due to the car. We only put the forces that are acting on the car. So keep that in mind to lessen the amount of confusion that you may experience when you're trying to do free body diagrams. We're just worried about the forces acting on the object. So in this case, the first one to add, and this is probably the case for most force diagrams, is the force of gravity, because most physics problems will take place on the Earth, and gravity is a force that is constantly acting to all objects on the surface of the Earth. Also, we know that the car, when it's at rest, is not going to be sinking into the road or flying up into the sky. In other words, the vertical net force on the car must be zero. And so if the force of gravity is pointing downward, there must be another force pointing upward, which we call the normal force. And in this case, the normal force is equal and opposite to the gravity force, so that their sum comes to zero. This is a way for us to describe that the car is not accelerating up or down. And since the car is at rest, it's not attempting to move left or right either. And we have no forces described as acting left or right. So this actually concludes the force diagram for a car that is at rest. Now let's think about a car accelerating. So I'll draw my car again. I'll also draw the road. Now once again we can put in our forces down and up. Here we have force of gravity. We have the normal force. Those are still there because the car is still made out of mass and it is still on the surface of the Earth, so it will still feel gravity. And the normal force will prevent the car from accelerating downward any further. And where does the normal force come from? It comes from the road itself. In other words, the road pushes up on the car. Now, if the car is accelerating forward, that means that the net force needs to be in the forward direction. In this case, I'm going to assume forward is off to the right. That means that there is a force to the right on the car. This is probably a force coming from the engine. The engine is ultimately responsible for moving the car forward. So we'll just call this F sub engine. Now, on a road, when a car is moving on a road, there may be forces that are acting in the opposite direction. The most likely of those is friction. For example, there is wind blowing this way and hitting the car. You'll also hopefully recall in your everyday experience that if you take your foot off the gas pedal, if the force of the engine goes away, the car immediately starts to slow down. You will notice that your speedometer starts to drop. That must mean there's some force that will push the car in the opposite direction. And we call this either just a generic friction force, or to be more exact, we can also refer to this, if we're talking about the air, as air resistance. Now, since we know that the car is accelerating forward, in other words, there's the direction of A, we know that the net force in the horizontal direction must point in the same direction as A. In other words, we know that the force from the engine, which is pushing in the forward direction, must be larger than the force of friction. That is the case when the car is accelerating forward. Now this changes when we talk about a situation of a car traveling at a constant velocity. So for example, if you are holding your speed steady as you're driving down the road, the speedometer isn't moving up or down, then we have this following situation. We still have the force of gravity and we still have the normal force. They are equal and opposite, so they remain balanced. But now we also have the force of the engine, and the friction force will end up being balanced. So let's note that over here. Force of the engine now equals the strength of friction. How do we know this? Because we know from Newton's first law that if an object has balanced forces on it, that means that it is not accelerating. And vice versa. This reasoning works the opposite way too. So if we're told that the car is moving at a constant velocity, in other words, we're told that there is no acceleration, we then know that the net force on the car in any direction must be 0. And so when you're holding the speedometer steady on your car, you're providing just enough gas for the engine to provide exactly the same amount of force as the friction on the car, just in the opposite direction. You might notice that when the car was at rest, we could also describe it as having no acceleration. In other words, whether an object is at rest or an object is at a constant velocity, we have a similar situation in that in both cases the net forces on the object all balance out. Alright, now let's talk about a car slowing to a stop. Once again, we draw the car, place our dot and put down the forces. Still have the force of gravity, still have the normal force. They still remain balanced. How do we know that? Because the car is still not accelerating either up or down during this entire situation. Now if we're talking about a car coming to a stop, that means that we know for certain that the net force is in the opposite direction. We know this because only when an object has an acceleration in the opposite direction as its current velocity will it start to slow down. So if the car is moving to the right, in order to slow down, it must accelerate to the left. What does this mean? Well, it could mean one of several things. For example, if you still have your foot somewhat on the gas, then there is still a force from the engine. We could draw it in here like this, F sub engine. But similar to what I mentioned before, if you start to take your foot off the gas pedal, then often you'll find that your car tends to slow down, especially when you're at very large highway speeds. In other words, at this point, the F sub engine is less than friction. So in this case, because the friction force is stronger, that leaves the net force going in the left direction, which means that the acceleration will also be in the left direction by Newton's second law. Another way that the car might be slowing down is if you're applying the brakes, in which case you're not touching the gas pedal at all. In that case, once again, still have the forces of gravity and the normal force. But in this case, if your foot is completely off the gas pedal, there is no longer any force to the right. And if you're applying the brake, then we know that both friction from the air and the force that comes from the brakes are both pointing to the left. That means that you have even more force this way, which means you have a stronger acceleration to the left. This is why applying the brakes will allow your car to slow down faster. In both cases, the net force is to the left, even though the car's velocity is currently to the right. And that's how we know that the car will be slowing to a stop. So this concludes this video example on free body diagrams. Thank you for your attention.